Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
I want to tell you a story that's somewhat difficult to convey. This is highly theoretical physics. You will notice that there are no demos, I'm afraid. The silver lining is that there also will be no formulae. So that means I'll have to try to do it with pictures. So I've called the lecture String Symphonies in the Sky. What I'm trying to convey is a relation which a lot of physicists are very excited about, at least a lot of theoretical physicists, between relatively conventional black holes of the kind that we see in the sky, but also some quite esoteric theoretical ideas that at the face value would have absolutely no relevance for what we see, but that we think has, if not relevance, then at least can shed some light on some of the mysteries in what we see. So let me start with just the very, very brief introduction to black holes. They're the strongest forces that we know of in the universe. They're strong, strong gravitational forces. At some level, there's no limit to how strong they are. They're so strong that they rip space and time. Space and time simply changes its nature from what it normally is. The black hole name is a very apt name. It really creates holes in the sky. So the picture is an artist's impression, but nevertheless is quite realistic for how we think about an actual black hole. There is the sky. Here, conveniently, there's also some clouds, as there often are outside the black holes, so we can sort of see the surrounding sky. And then there really is a hole. There really is a hole. And the hole is what it looks like. It's like a sink. It means that if somebody falls in or gets near, they simply can't escape. And this is why. It's because there is a hole in space. There's an absolute sink. The forces have no limits. You just can't get up. The space is exorcised. So black holes are black. And they are black basically because not even light can escape. Nothing can get out. So if there's no light, well, they're black. So that's why they're black. They're holes, and they're black. So there you go. It's a great name. We are indeed welcoming our prospective grad students. We need new ones. So, well, nothing can get out of black holes? Well, almost. Almost. There is a but here. This is where the esoteric physics comes in. Quantum mechanics of the kind that we don't normally associate at all with astrophysical phenomena because those are so big. Normally we think about quantum mechanics in the context of atomic physics, for example, of the atomic model. Quantum mechanics tells us that all objects actually have a little bit of an intrinsic uncertainty. Wherever they are, they don't really know where they are. Approximately, objects know where they are, but there's some intrinsic microscopic uncertainty that simply can't be removed. It's there. Normally, the way we think about it is in the context of atomic physics, where, for example, this atomic planetary model on the top picture there, which is the one that maybe we first put in textbooks for students or put in, the newspaper or wherever else you try to find a little picture of the atom, you'll say, oh, there's a central little nucleus and the electrons are nice orbits around, much like a solar kind of system. And this is true at some level, but a slightly better model actually is that these electrons aren't really going in strict orbits the way the Earth is around the sun. Instead, they kind of wave their way around. It's as if there really is an entire kind of blobby wave that's going around. So the lower picture is a much more accurate picture of what an orbit is for an electron around an atom and around the nucleus. What I want to try to convey is that at the quantum mechanical level, at the very microscopic level, we're very accustomed to the idea that no object really knows exactly where it is because a wave doesn't have a precise position. it kind of is spread out. You can't have a point that's wavy. Necessarily, the wave is kind of stretched out and has a middle point, but it's stretched out. Well, this principle, the quantum principle, it acts everywhere. The nature really is quantum mechanical. It's just that normally we don't notice, because for very big objects, like humans, or other macroscopic objects that we can readily see, quantum mechanical effects are very, very small. And in particular, for black holes, they're very, very tiny, because those are much bigger even than humans. They're enormous. So black hole effects on quantum mechanical effects on black holes, of course, very, very tiny. But yet, there's an issue of principle. Quantum mechanics is an actual fact of nature. It works for atoms, and it works for everything else. Just normally, we don't notice it so much. So this is where Stephen Hawking comes in. Stephen Hawking is, of course, famous for very many things. He's probably one of the most famous living physicists, written many popular books, appears often in the newspaper. One of the important things that he has discovered, perhaps the most important, was that he realized that once you take into account this quantum uncertainty, it's really not true that you can't escape a black hole. Some things can escape a little bit. It's a tiny effect, it's very little. That sometimes the quantum uncertainty means that matter that is falling inside doesn't quite know if it's inside or it's outside. In other words, it doesn't really know if it's supposed to be absolutely impossible to get out or whether it actually is possible to get out. That's kind of important. It's true that it's just a tiny effect, it's just an issue of principle, but it matters whether can you escape or can you not escape. In fact, the picture he found was that the stuff that randomly can perhaps get out of the black hole, it makes the black hole look as if it's thermal, as if it's kind of burning, as if stuff for quantum mechanical reason can get out, and the black hole in fact does not look exactly black. It looks like a burning object, one that's sending out radiation, just the way a thermal object would, you know, a hot piece of coal or something like that. So that the black holes are in fact not black at all, they're thermal. This emission rate, I should caution, is extremely tiny. I've emphasized already that quantum mechanics is something that normally is significant for atoms. For black holes and such, it's really tiny. But still, it's there. It's an issue of principle that these black holes are not black. They're in fact kind of like thermal objects. And that's one of the big clues that keeps quite a lot of researchers, including myself, quite intrigued and that we work on. And as I told you, this radiation, it's rare and it's thermal. The reason that is so intriguing is that thermal radiation, or anything thermal actually, comes about in a very special way. Thermal energy is not just any other energy. It comes about for statistical reasons. It comes about when a large number of objects, like air molecules in this room, they have some energy and they share it in a totally random way. When something is thermal, what you'll know from it is that it's some object that itself is kind of made out of a lot of little things. You may not know what the little things are, but you know that when an object is thermal, it somehow is because it's having energy that's being shared between all its constituents. So when we see a thermal object in physics, what we conclude usually is that there somehow is an ensemble of microscopic objects. Those microscopic objects, like the molecules in this room, in this case we actually know what they are, but then they share somehow the energy, and they share it in a random way. Occasionally one of them has a lot of energy, maybe some of them has a little energy. In average, they have, well, the average energy, but they share it. So this is the standard example. Gas in this room, solids, other things made of atoms. But the theoretical question of principle that have intrigued me, at least, for many years is what exactly are the constituents that give rise to thermal behavior of black holes? Black holes look like just holes. They're sinks, they're holes in space, they are nothing. How can they somehow manage to make thermal behavior? How can they manage to behave as if they're made of a lot of little things? And besides, what are these little things? There seems to be nothing there. This is a very important point of principle. So let me try to basically repeat it on a separate slide. Statistical physics is this insight to thermal behavior. It reflects energy shared between many constituents. Right? Normally we think about air. I've said it at least once already, but probably twice. It's a model, the picture there, all the red dots we think about as molecules. They might be just moving around. I should have gotten the image to move, but I didn't. We think about it as the molecules moving around in the room. The little blue one is just following a specific one that follows the blue trajectory. But the point is that the behavior that we see in our macroscopic world with our eyes, it comes about because there are so many microscopic constituents. And what we ask in the case of the black holes is, what exactly are the constituents that give rise to this thermal behavior? This is where some theoretical physics comes in. There is an important clue. How many constituents are responsible for this thermal behavior that the black holes have? Well, the temperature of the black holes one can compute. It was one of Hawking's insights that he not only realized that quantum mechanically things could somehow make it out of the black hole, but he figured out exactly how often does it happen. It doesn't happen often, it's rare, but how rare? You know, what is the rate by which this happens? So he figured out, in short, that would be the modern way of saying it, is that what is the temperature of the black hole? Well, it's tiny. It's very tiny, like 10 to the minus 6 degrees. Pick Fahrenheit or Kelvin as you wish. It's very, very cold, okay? Above the absolute zero. It's very, very cold. It's the sort of thing that when you see pictures of black holes in newspapers or wherever else you might see them, you will see a big cloud maybe that's spinning into the black hole and that's giving out thermal radiation, often with thousands of degrees. It's very hot gas because it gets whirled in. It's not what we're talking about here. We're talking about the tiny little quantum effect that is totally being swamped by these big clouds that happen to surround the actual black holes. But it's this little quantum effect that keeps us intrigued. Because this very, very small temperature for such a giant, giant body, you can mathematically show is only possible if the number of constituents of that body is humongous. Is humongous. You can simply compute how many constituents do you need for the vibrations and the fluctuations of this to give rise to this particular thermal behavior. And what you find is that a large black hole, like the one in the center of our galaxy, has as many constituents as the entire universe. Now, this is crazy, right? I'm saying that there's a single object, the black hole in the center of our galaxy, that's made out of little things. I don't know what the things are, but I know that they're made of so many things that it's as many as there are atoms in our entire universe. Not just our galaxy, the entire universe. No, there's 100 billion stars in our galaxy. There's another 100 billion galaxies in the universe. All of that gives as many atoms and degrees of freedom as a single black hole. Of course, you would say that, well, aren't there many black holes in the universe, and therefore the entire universe has more sort of constituents than just the atoms? And you would be right. It means that the majority of all constituents in the universe sit in the black holes, and all the stuff we see and that we keep track of, if we're astrophysicists, all the atoms, are in fact irrelevant when it comes to what are the true constituents, what are the number, where are most of them. They're in the center of black holes. They're in the center of black holes. So this is a number that's intriguing because it's so big. So this reveals that the number of degrees of freedom, these microscopic constituents of the black hole, is just so unusually large. For example, they're not just the atoms that went in to make the black hole. A lot of atoms made the black hole up, of course. These are big things, so they're made of very, very many atoms, but not enough at all. Not enough at all. The degrees of freedom, the number of constituents that are being revealed by these slight thermal effects, is much, much bigger than that. The interpretation that physicists have made of that effect is that what is happening is that these gravitational forces, which, as I said in my opening line, are very, very strong. They're so enormous that they crush the material. And it doesn't take much imagination to imagine that the atoms themselves get crushed and get crushed into their microscopic constituents. And those microscopic constituents somehow are particularly numerous when you smash something into its very smallest microscopic fundamental constituents. Well, presumably you get more out. So that's the idea. The black holes somehow are so strong that they manage to reveal for us what are the smallest constituents when you, with arbitrarily big, with almost infinite big force, squash the objects apart. What do you get out? And in particular, how many microscopic constituents did you get out? So we know, in a way, from this long, indirect argument, we know how many fundamental constituents there are in matter. And that's very exciting to people, the physicists, that are thinking about the fundamental nature of what nature is all about. So now, we should take a whole other detour. We should say, what is it again with the fundamental constituents on matter? It's an entirely different question, philosophically speaking, that has been asked since ancient times. It has nothing to do with black holes, it's nothing to do with the sky, nothing to do with astrophysics. It's simply, well, the stuff we see around us, what is it made out of? Well, the ancients already posited that it's made of atoms. It took a few thousand years to establish it, but nevertheless, that's what we normally say. Everything is made out of atoms. It actually isn't true according to the modern picture, because indeed, even this drawing that I already put up reminds us that atoms themselves are not really fundamental the way the Greeks thought. No, they're themselves made out of smaller things like electrons and nuclei, the central nucleus and the electrons. But okay, it's made out of sort of little things. That's what matter that we see is made out of. We are accustomed to the idea that what we see as matter is not fundamental, it's made out of little things. Those little things are, well, atoms, and this is the eternal structure of atoms. Oh, and then what are atoms made out of? Well, the modern understanding is that the fundamental constituents is not just made of matter, because atoms are indeed made of these nuclei and electrons, but what when you go further in, then these nuclei, the center part of the atom, is itself made out of, nucleons, protons and neutrons in other words, the things that nuclei are made out of. And those nucleons, the protons and neutrons, are themselves made out of quarks. And we can certainly imagine that, what are quarks made out of then? What are electrons made out of? Yeah, true. What are the true constituents of matter? We're trying to look into that very question. All right, this is what is very, very fashionable and, of course, extremely exciting experiments going on at this point at CERN in Geneva, at the LHC machine, is to find out what exactly is matter made out of. At the fundamental level, at least that's the fundamental level that we're trying to seek very explicitly. We take an enormous ring, 27 kilometers in circumference. We'll make a big machine that is designed to take nuclei, nucleons, protons in this case, to smash them together at as high energy as we possibly can. And then when you do that, you smash things together at the highest possible energy you can. You hope that they break. And when they break, fundamental constituents might emerge. So you construct giant detectors to try to see what fundamental constituents might come out. And maybe, if you're lucky, you hope that we can find constituents that are smaller than the smallest constituents we've identified so far. And if we succeed in that, we'll say we make great progress towards making it in towards the more fundamental degrees of freedom. So that's the strategy. Now this, as it happens, is a side issue for me. It's not what I'm talking about. Because you see, this is the violent approach. I'm a theoretical physicist. I'm not like these violent Europeans. The alternative is to think. So let's suppose that electrons and quarks, in fact, really are fundamental. That, okay, we're at the end. Whatever theory has found so far just happens to be the end. And in fact, this whole violent machine was built in vain. That's a little bit of a depressing thought, but let's take it for a minute and say, okay, these are maybe the very, very fundamental degrees of freedom. This is the smallest stuff there possibly could be. Let's imagine that. Operationally, what would that mean? Well, that would mean that these objects, the quarks, the electrons, would not have any internal structure themselves. They would not be made out of any smaller stuff. Could this possibly be true? It would mean that if we collided them against each other at however large energy we had, not maybe just even at the LHC machine at CERN, but even bigger machines, whatever big machine, a light year across you could imagine, because imagination is boundless. However much energy you could possibly imagine. If I'm going along with the thought that these are fundamental, I would say nothing would break these things apart. Could that possibly be the case? Well, the thinking is that this cannot be right. It cannot possibly be that these objects are the most fundamental. And it's due to Einstein's famous formula, E = mc squared. If I have arbitrarily much energy available to me, which is what I'm imagining in this thought experiment, I would always be able to break them apart and basically create constituents that were arbitrarily massive. This corresponds to being at smaller and smaller scales. And if that were to happen, particles at very high energy, they behave as if they're very, very large mass. So for sufficiently high energy, these protons that we'd be scattering against each other, they would actually create a very, very small region with a lot of mass. If you put a lot of mass in a very, very small region, you get a black hole. But black holes are made out of stuff, you know. We've already been through that. So somehow, when gravity enters the picture, it cannot possibly be that these objects really, truly cannot somehow be made out of something else. Somehow, there's something wrong. Now, what I'm talking about is not this. This has been a lot in the news, right? That if we imagine we scatter at enormously high energy these protons, like at the LHC, you could worry. And there are some people that have looked at satellite pictures over Geneva very carefully. Here they've spotted Lake Geneva, and something strange is happening at the end. Things have been scattered together, and I guess Geneva disappeared. This is not clearly what we are talking about. I'm a theoretical physicist after all, and besides, people at CERN are very, very careful. They've taken extreme precautions, all right? In fact, particles like electrons, quarks, and such, they're so light that normally people at CERN and other practical physicists that build accelerators, they're arguing and thinking that, well, look, gravity is entirely negligible. These particles have very interesting forces between them. They're electrically charged, for example, and the electric charge makes them repel or attract. They have other interesting forces, nuclear forces of various kinds. They may even have unknown forces that one would like to try to explore using these accelerators. But the one force that people are usually entirely uninterested in is gravity. It's totally negligible. It's negligible because these particles are so light. Even at the energies that we manage to accelerate them to, their effective mass, the gravitational force between them, is entirely negligible. It really isn't important. The value of this Planck energy, that is the energy where one can imagine that we'd have to go to before the elementary particles themselves would really create giant forces and turn into black holes, is much, much bigger than what one is able to have at CERN. It's 10 to the 18 GeV, which is 10 to the awfully many zeros behind, times the energy that's available at that accelerator. This is why we're not nervous at all that black holes would be formed at an accelerator just like that. What I'm after is a principle. It's the principle that these elementary particles that we've identified, they cannot possibly be fundamental. They really can't be, because theoretically speaking, it just couldn't possibly happen. This is the revenge of gravity. Gravity is being neglected by particle physicists, but theoretical physicists like me would say, no, no, it will always win. Gravity will always win in the end. The end may be far away, but it will win. Oops. Wrong way. Right. So again, electrons, quarks, those things, they cannot possibly be fundamental. So what happens at very small distances? Well, the things we imagine and those things we see, they could be made of something else. They have to be made of something else. The first step is that we say, well, they could have been made of even smaller things. Maybe quarks are made of even smaller particles. Yes, yes, this is true. But then what would those be made out of? And if you found out of that, what would be those be made out of? The only known way to circumvent that you simply just keep going down, 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 and whenever you say, this is the fundamental stuff, some pesky theoretical physicist would say, well, but if you go to high enough energy, wouldn't black holes be created? And black holes, you see, are made out of something, so this is not fundamental. The only way that we know out of this conundrum is to instead posit that particles are simply not the fundamental things. The fundamental objects that constitutes everything that we see somehow should be strings. They should not be strings. They should not be particles. They should be strings. They should be something that is extended, that itself has a distance in it. This means that when we add energy, then instead of what happens with a particle is that, well, the particle kind of gets more and more massive because it gets more and more energy, and in the end it might create a black hole. But instead what happens with a string when you add more energy is that you add more vibrations to it. It has a different thing that it can do with the energy. It doesn't have to just bulk up and basically become fatter. It can become more vibrational and actually take up more space because it vibrates more and more violently. If it takes up more and more space, then it's not in danger of making a black hole. So the only theoretical way we know out of as simply proposing anything that is truly fundamental is to take a string and posit that that is the microscopic, truly fundamental object. It's the only way we know around these concerns. So this is the idea. We take big objects, a flower, that's the poetic thing. They're made of carbon atoms. But the carbon atoms, what are they made out of? Well, in the picture we see they're made out of the usual atoms. They have a nucleus, they have some electrons around, 6 electrons in this case, and mostly carbon atoms. And the carbon atoms are made out of, well, electrons and nucleus and nuclei. The nuclei themselves made of nucleons. The nucleons are made out of quarks. But what are the electrons and quarks made out of? Well, they're made out of strings. When you go to the next level, you see that they're made out of strings. They're made out of different vibrational pattern of a different kind of string, so that the fundamental string that's being theorized here is one that can vibrate in many different patterns. And some of the simplest patterns would be the patterns that we see and interpret as elementary particles. The string would vibrate in a size that is so small that we think that the particles look as if they are really particles, but in fact they must have a little length, or else they would somehow create black holes if we collided them at sufficiently high energy, and then they wouldn't be fundamental. So therefore somehow the most fundamental object, as far as we can tell, must somehow be a string. The simplest vibrational pattern of this theoretical string is gravity itself. The simplest pattern is a gravity wave. Gravity waves are thought to be very, very real. In the picture on top, they're taking two black holes that are very rapidly spinning around each other. When they spin around each other, they're yanking the gravitational field as rapidly as they can around, and that stirs the gravitational field and makes big waves in the gravitational field. Those gravitational waves have a very characteristic vibrational pattern that modern experiments are in fact going and look for, these vibrational patterns. I'm not going to go in that direction and review those experiments, in part because there have been other talks about this actually in this series. But from my point of view, it's intriguing that the simplest vibrational pattern of these actual gravity waves are exactly the simplest vibrational patterns of a string. The picture on the left and the bottom is the evolution of a graviton excitation of a quantum string. It's really like taking a hula hoop ring and bouncing it. You know, it goes in whatever directions it can. You squeeze a little bit on one side, it goes out on the other. It stays the same size. And the gravity waves that people actually look for in real experiments take patterns. On the right-hand side, here's a set of pearls that basically people are measuring the distances between these different pearls in order to find what is the vibrational pattern of a gravity wave. So the gravity wave has a very direct relation, an interpretation in terms of what we think are the fundamental string degrees of freedom. Well, so string theory is a theoretical response to a theoretical problem. It's exceptionally principled, as I try to emphasize, is pursuing the principles of the situation. And, well, it's not practical at all. Many string theorists are famous among their peers, among their more practical and experimental peers, for being not so particularly practical. And in short, that does mean that it's very difficult to test string theory. It's very difficult to test string theory in any kind of real sense. Except we might go back to the original ideas, to the black hole. I went on this detour trying to review briefly what exactly the thinking on fundamental objects of the kind that we look for in large particle accelerators. Well, remember that strings, they were kind of posited as the solution to a theoretical problem. What could matter possibly be made out of at the very fundamental level? Sure, quarks and electrons could be made out of something smaller yet. That itself could be made out of something smaller yet. But in the end, somehow the thinking is, we need something that itself has a fundamental distance. And that's where the strings came from. The principal solution to a principled problem of what is fundamental constituents of matter. But there was another principal problem, the one that I actually reviewed first. This thing that the quantum theory of black holes revealed itself a principal problem. It reveals that black holes have numerous constituents, enormously many constituents, in fact, many more than you would possibly have imagined. You would have imagined that the black holes would be squashed into matter, into its atomic constituents. Maybe its atomic constituents would be squashed into its nucleon constituents or its quark constituents or whatever. But however far you follow that line of thought, somehow the black hole is squashing them even further. They are squashing them even further and revealing even larger number of constituents than you could possibly imagine. So that was a theoretical problem. And it's by putting these two theoretical ideas together that we can find a test. It's a theoretical test. But we can try to employ the black holes and the conundrum they pose to test string theory, and vice versa. Use string theory to test the quantum structure of black holes. So this is the idea. The proposal is that black holes can be described either as a hole in space, which is the traditional way of describing it, is that it's literally a hole in space. That's the left side of the slide, the conventional description of a black hole. You have space, nicely with coordinate lines so that we can see it, and then somehow there's a hole. So simply there's nothing left. Okay? But there's another description, the one on the right. A string theory description where roughly the same region, some spherical region, is described as a huge number of vibrating strings. These two pictures do not look alike at all. It's not intuitive at all that these two should be in any way related. But what the theoretical idea is that both these descriptions are correct. And in fact, at least for somebody not as unfortunate as to enter the black hole, there's no way of telling them apart. These two things, for somebody who's outside the ball of strings or outside the hole in the space, there's simply no way of telling these two pictures apart. They will look the same. How does that work? How could this possibly work? Well, the evidence for this equivalence between two dramatically different descriptions, one that's fundamental in terms of the strings and one that uses space-time and its holes in it, is that the temperature and the number of constituents of the black hole, they depend in complicated ways. I told you that there were many of them, but exactly how many depends on how big is the black hole, what is its mass. It depends on its angular momentum, as in how much is it rotating, what is the amount of rotation of this black hole. The formula for how many constituents are expected is quite complicated in its dependence on these different parameters like masses and angular momentum. But it's given by the same complicated formula in the two different descriptions. Whether you describe the black hole as a hole in space and try to analyze how much quantum radiation does it actually emit, what exactly is its temperature as a function of how much mass, how much rotation, how many other parameters might you have. If you instead say, oh, I'm just going to think about this as a big ensemble of strings, numerous numbers of strings, each in any arbitrary vibrational pattern, but exactly how many vibrational patterns will depend on exactly how much energy you have to share between all the different strings, and how much rotation should the strings overall have. And this, you can compute now how many vibrational patterns are there, how many fundamental possible constituents are there, and you get the same complicated formula that you get from the description in terms of space. The amount of thermal radiation you get from this radiation, from these two different descriptions, is also the same in the two different cases. The description is very, very different in the two cases. In the first case, you have sort of the left picture is sort of a space-time picture where you have a hole in space. I put a bunch of trajectories on it. Frankly, it's because this picture, it just makes the black hole look entirely stringy. And it's such a nice picture, but it really is not the stringy description at all. The stringy description is much more like the right-hand picture. It's saying that the region that has somehow been exorcised from space, that doesn't exist, somehow will appear as if it's some kind of surface, and this surface has a lot of strings on it that are vibrating in all sorts of patterns, but sometimes the strings will get released. And when those strings get released, we see that as this tiny quantum thermal radiation that exits from the black hole, and it's the fact that these two descriptions give the same amount of thermal radiation, no matter how big, how massive the black hole is, no matter how much it rotates, no matter how much charge it has. It's the fact that these two descriptions give us the same, that give us the confidence that somehow these are two different descriptions of the same object at the quantum level. So this is what string theorists, at least, are very excited about, and what we feel is a very significant triumph. The string theory has all these possible vibrational patterns, and it has exactly, in the end, the right number of constituents of different vibrational pattern. Each vibrational pattern is thought about as being sort of like a different particle, really, except that the higher vibrational patterns become fatter particles, bigger particles. We have exactly the right number to make up a black hole. And ordinary particles just cannot do that. They just cannot do that, because whatever number of ordinary particles you were to posit would exist, they always would be point-like. They always would be arbitrarily small. Once they're arbitrarily small, it gives us theoretical problems with what happens when we smash them together at enormously high energy and start probing these arbitrarily small energies. It simply cannot work. This is why string theory is the only candidate we have for a totally fundamental theory of what really happens at the very, very smallest scales. It's the only candidate, at least, that we know of. There could be others, of course. So this is where we stand. It's the only thing we can think of that could possibly be fundamental. We think it responds to this theoretical problem, whichever side we come from, whether we come from saying that, well, what is matter really made out of at a fundamental level? Or whether we say, well, what are black holes really made out of at a fundamental level? We think the answer to the two questions are the same. And since string theory seems to somehow get a connection there, we feel that that amounts to some level of evidence for string theory. But it's not exactly practical, as I mentioned. It's something that say, well, okay, what does that mean for nature, for actual experiments? Well, that's hard. The only way we can think of trying to test these things for why do we care is really not going, in my opinion, so much for trying to see, well, what do experiments that we see really show us? Will they show the strings coming out? I don't think they will. But we can go in other directions and try to test the theoretical concepts. The string theory description of the black holes is identical, as I mentioned, to the conventional one, but only as far as observations outside the black hole is concerned. This is where the grad students come in. We need somebody to probe inside. Just kidding. But it's true that the description inside and the black hole interior will be different according to whether you describe the black hole as a hole in space or whether you describe it as an ensemble of strings. All you need is somebody that sort of probes inside. Why would I possibly care about that? Well, again, I go to my theoretical foundations and saying, well, what exactly happens in the interior? One of the things we're really puzzled about in the description as a whole, description of black holes, is that it looks sort of like a hole, yes, but then as you go all the way down, you say, well, where's the bottom of the hole? Is there a bottom? Well, yes, there is. And that bottom is kind of like a trumpet. There's a singularity at the end, where space itself is kind of totally moving in and becoming arbitrarily small. And you'll say, well, there's something wrong here. Space itself cannot pinch off and become just sort of a point like that. That's called a singularity. It means that the description of space itself is some kind of something smooth, more like a membrane, some rubbery substance or some such thing that we normally think about space as something that's just there. Somehow when it crumbles up and becomes just a point, the standard description of space simply is impossible. So there's a problem, a theoretical problem again, when you go to the center of the black holes. The right-hand illustration has another illustration of much the same, that there's sort of the circle around. The light circle corresponds to the area where light is either being pulled in or shed out, if we're talking about the Hawking radiation, the thermal radiation. But then in the very center, there's a singularity. There's some little black thing that we just don't know how to describe using any kind of theory that we know of, or at least any of the standard kind of theories. But string theory does not have a singularity like that. String theory is able to describe the interior as an ensemble of very large numbers of fundamental constituents with very, very many vibrational patterns. It would still be an exceptionally violent place to be because there are so many objects in there. So it would not be a pleasant place to go and explore, but nevertheless, it would not be a singular place. This would be a regular description of something. So it's something that theoretical physicist feels is progress after all, because if you previously didn't have a description that at all described what would happen in the very middle, now you have a description that does describe it. Well, that's called progress, even if it's a kind of progress that you can't actually test at the face of it. So to go for a test of this kind of thing, what we're thinking is that you should go instead not to think about black holes in the sky, but instead of thinking about Big Bang cosmology. Because Big Bang cosmology has a theoretical problem that's very, very similar. These apparently infinite gravitational forces that there are at the center of the black hole, they're analogous to those apparently infinite forces that afflict the Big Bang theory. You should recall that the universe is expanding. It's expanding now, and it has been for 13.8 billion years, give and take a few. So it used to be smaller, since it's expanding, and it used to be smaller and smaller and smaller the further back you go in time. And it used to be hotter. As you go back in time, it kind of heated up. So, as one follows the history of the universe sort of all the way back, if you will, then its size, it vanished. It became a point. The temperature became infinitely big. It's the kind of description that says, well, space and time somehow disappeared. Clearly my vocabulary for talking about it, my way of thinking about it, somehow does not work at all. This is what is called the Big Bang singularity. It's the very, very origin of the expanding universe. It's a place where we have no theory that describes it. This is worse than having wrong theories we can test and find that they do not compare correctly with experiment. We simply have no theory for that very early spot. And that means that we cannot even start comparing it with any kind of experiment. The hope is that in this Big Bang singularity, string theory can also address that. The string theory, because it is quite successful in addressing the singularity of the black hole in the center where the gravitational forces become infinite, it should be possible also for Big Bang singularity to be addressed, to somehow describe the Big Bang singularity itself as the place where the smallest constituents of the universe, they enter into action, and it is those that somehow set the initial condition that is responsible for starting the bang and for starting the entire universe. A very important problem, to say the least. The hope is that this Big Bang singularity has some kind of sensible description in terms of strings, and that is a very active area of research, although, truth be told, is not one where I would say we have at this point any kind of actual, theory that would give predictions, but it is this that in my mind is the answer to why do we care? Why is it that it's so important to address these theoretical problems that the quantum black holes are posing and that the smallest constituents of the universe are posing? So this is the status. I'm almost done, 10 minutes early. I had warned people, but they said as long as it wasn't 15 minutes early, I'd be fine. The status of string theory, as far as I'm concerned, is that the fundamental constituents that drive this origin and the current expansion of the universe, they are something that we don't really know what they are, but the fundamental constituents is really the only candidate we have for that are strings. Point-like constituents simply will not do the job. They simply will not do the job. So string theory, they could be fundamental. And since they could be fundamental, this is something we have to pursue. And as we pursued this theoretically, the best evidence we've found so far that we somehow are on the right track is by comparing with the black holes, by comparing and finding that the vibrational patterns of the string, they correctly account for these numerous constituents that you need to understand the quantum black holes. So it is for that, at least in my mind, string theory is compelling, and it needs to be developed much further. So here you are, the string symphonies in the sky, North Carolina String Quartet. The only picture I could find with a black background that would fit. But I'm halfway serious with the picture, as I hope you understand by now, in that what I'm saying is that this really shouldn't be one picture. There are two descriptions of this hole in the sky. Either you think about it as a hole in the sky, or else you think about it as a huge set of strings. And as long as you stay outside, either description will in fact amount to much the same thing. Thanks for your attention.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.